Hey, welcome back. Today we're working with power series. So in the beginning here, the book is going to note, in the previous section, we kind of approximated um, these functions with these polynomials. So e to the x can be approximated with the polynomial 1 plus x squared all over 2 factorial plus x cubed all over 3 factorial. You can get a fourth degree x to the fourth over 4 factorial. It's going to turn out that uh, the longer the polynomial, the better the approximation. So somebody figured if you take an infinitely long polynomial like this, and just keep on adding and adding forever and ever, so you end up with this infinite sum thingamajig. So maybe go from n equals 0 to infinity of x to the n all over n factorial. Hopefully that thing equals e to the x, okay? And we will find that in fact it actually does. There's some outstanding questions on that, though. There's questions like if it doesn't equal it, are there certain x's where it will equal it? So there'll be kind of a radius of convergence for some functions. It turns out that this thing will converge to e to the x for all x. But in general, that's not always going to be the case. So you'll be able to kind of approximate things like, I don't know, 1 all over 1 minus x is approximated by the series x to the n from n equals, what is it, 1 to infinity maybe? Well, let me just say it's equal to that. We'll worry about the indices later. This is true, but it won't be true for all values of x. It's actually only true from -1 to 1. So if you go outside that interval, that approximation won't hold, and this thing is called the interval of convergence. Okay. And basically, it's kind of the interval of usefulness, right? You can approximate the function with the series in a particular interval, but outside that interval, it won't work. Okay, so interval of convergence, but I kind of think of it as the interval of usefulness. Okay, and anyways, in order to kind of, I guess, eventually study this phenomena, we'll introduce power series. So this guy right here is a power series. This guy right here is a power series. And we want to play around with those and kind of figure out their intervals of usefulness just in general without actually connecting them to their corresponding functions, right? So for the time being, we're going to forget about this idea that we can use these series to get approximations and even in some cases use them interchangeably. We'll forget about that for a second and just worry about this interval of usefulness. And so we're going to be studying these series kind of away from the functions that they'll eventually represent. And these series are called power series. Okay, so section 1, the power series. And essentially, it's just a regular series. So the kind of series we've been studying, n equals 0 to infinity, maybe of, let's say, -1 to the n times n factorial times x to the, or times 1/2 to the n, right? Okay, so this is the kind of thing that we've been studying in 9.2 to 9.6. So this is like a before and after picture here. So before, we're looking at that. Now what we're going to do is kind of replace that number with just a variable. And you can kind of think of it like, moving from arithmetic to algebra. It's kind of the same idea. So we'll just replace that 1/2 to the n with an x to the n and start studying these critters, and just effectively you'll be able to kill a bunch of birds with one stone. So you won't look at series individually. Instead, you'll look at these now power series and find the interval of convergence. And then if somebody gives you one of these before pictures, you'll be able to say, well, that's that 1/2 is in the interval of convergence, therefore this thing converges. So anyways, what are these things then? These things with variables in them instead of the numbers, they're called power series. Okay, so this right here is a power series now. And we want sort of a general representation of a power series. So in general, we will say a power series basically has the form of an infinite polynomial, infinitely long polynomial. So starting at n equals 0 to infinity of a sub n x to the n. Okay, so in the above case, this portion here is a sub n, and then you have that x to the n tacked on. And of course, you can have the kind of shifted power series you see there on the right. That thing, you just put x minus c instead of x. Okay, no big deal. Sure. So anyways, there's the power series. And again, we're interested in basically for what values of x is this thing useful? For what values of x does this thing actually converge? And that becomes the idea of this radius and interval of convergence. So section 2, the radius we'll look at first, and then the interval of convergence. So it'll turn out for the radius of convergence, it's not going to be kind of like a spotty convergence. So it's not going to converge at x equals 1/2 and then x equals -10 and then x equals 5. It's not going to be like that. It's going to be an interval on which it'll converge, and then for the interval of convergence, you have to kind of check endpoints. And that so anyways, the radius convergence will be kind of an interval, and the radius is just the length of half the interval. So you can imagine that this thing is a circle. If you were to kind of continue on from the where the parentheses are, and you're looking for the distance from the midpoint here to the outer point, that's the radius convergence. The interval of convergence will tell you these actual, if the first place is A and the second place is B, your interval of convergence might be something like the interval from A to B, maybe including A but not including B, right? So the radius over here would be 1/2 of the distance between A and B. Okay. But anyways, there's 3 kinds of radii. The first kind, the series only converges at the center. Okay, so the series converges only at the center, x equals c. And that's kind of the lamest type of convergence. When that happens, you'll write r is 0 for the radius is just 0, right? There's basically nothing there. Secondly, then, there's some interval. So the series converges on an interval around the center. We would have something like the interval from c minus r to c plus r. And then later, for the interval of convergence, we'll have to check the endpoints of that interval. But the radius then is just going to be whatever that r value is. Okay, so I guess r equals r, to be determined. Then thirdly, the radius is infinite. It converges everywhere. So it'll turn out that the exponential power series, the power series representation for the exponential function, will converge everywhere. So it's a real nice version. Anyways, the series converges absolutely. For all x. Okay. To determine these radii, we use the ratio test. Okay, so the workhorse. How do you spell horse? It's been a while since I've had to write out the word horse. The animal. Okay, workhorse. There's no A in horse. I don't know what I'm thinking. Trying to spell house and horse at the same time, I guess. I don't know. The workhorse is the ratio test. Okay, so yeah, that's what we'll be using. Let's see if they have some examples here in the book for us. Okay, so we have example 2 here, and we are given the series n factorial times x to the n from n equals 0 to infinity. We want to find just the radius of convergence. So we go to the ratio test. Remember, the ratio test is based off this number r. And basically first, if r is less than 1, then it's absolutely convergent. If r is greater than 1 or r equals infinity, then it's divergent. Thirdly, if r is equal to 1, then you have to kind of try something else. And that case will happen when you're looking at the sort of second case in the intervals of in the radii of convergence, and you have to kind of figure out what the endpoints are. So if r equals 1, it's kind of inconclusive, and you got to try something else. So that becomes kind of annoying, but anyways, let's take a look, right? So r is going to be equal to the limit, and now you need the absolute values. So in the previous problems when we looked at the ratio test, you usually didn't need the absolute values, but now you will. So a sub n plus 1 is n plus 1 factorial, x to the n plus 1, and then all over n factorial times x to the n. And it's always as n goes to infinity. If I'm not writing that, it always is. So anyways, we can brute force this guy. So n plus 1 times n minus 1 dot 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 all the way to 3 times 2 times 1. N factorial is n times n minus 1 times n minus 2 dot 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 all the way to 3 times 2 times 1. X to the n plus 1 over x to the n is x to the n plus 1 minus n, which will just be x. So using your rules of exponents, you can remove the n factorial portions, and so you're then left with the limit of the absolute value of n plus 1 times the absolute value of x. So remember, with absolute values, if you have the absolute value of a times b, that's the same thing as the absolute value of a times the absolute value of b. Then, because x is not kind of dependent on n, you can move the x out of the limit. So you can move this x out here, and then kind of just consider the limit of n plus 1 as n goes to infinity. This limit then will go, of course, to infinity. So for all values of x, almost all values of x, this r value will be infinity. There's one exception to that rule, of course. That's when x is equal to 0, which is the center of this particular power series. Okay? So the radius of convergence in this case is just 0. Because if x was 0, then that would effectively cause the limit. It'll be 0 times something inside of the limit, and that will be 0. Okay, so the radius of convergence is r equals 0. So it diverges everywhere except at the center. Yeah. Okay. Let's look at the next guy. And this is example 3. Okay, so again, we're finding the radius of convergence. I have the series 3 times x minus 2 to the n from n equals 0 to infinity. And I go to my ratio test. So I have the limit, the absolute value, 3 times x minus 2 to the n plus 1, all over 3 times x minus 2 to the n. Rules of exponents, so you just subtract when you're doing a quotient there. So the 3's will cancel. I get x minus 2 to the n plus 1 minus n, which will just be x minus 2 to the 1. That's just a constant with regards to the limit, because the limit is dependent on n. That thing inside the limit right now is not. So you could factor it out and just pretend it's x minus 2 times the limit as n goes to infinity of 1. And the limit of constant is just a constant. So you end up with x minus 2. Okay? Absolute value of x minus 2. So the ratio test tells us that this thing will converge when r is less than 1. So you make this inequality, you say, okay, it's going to converge when the absolute value of x minus 2 is less than 1. You can expand that into a compound inequality, so you go from -1 to 1, add 2 to all three sides, you go 1 less than x less than 3, and so on the number line, you know, here's 1, here's 3. For the interval of convergence, you basically need, or sorry, for the radius of convergence, you need the length of half that interval, right? So the radius of convergence in this case will just be 1. Okay. Later we'll have to check the endpoints in order to get the interval of convergence, right? So the interval of convergence will go from 1 to 3, but then we have to check to see the behavior at the endpoints. Okay, so that'll be a bit more work. But anyways, the radius convergence is just 1. All right, let's look at example 4. So we have the series -1 to the n times x to the 2n plus 1 all over 2n plus 1 factorial, going from n equals 0 to infinity. Alrighty then. So again, ratio test, limit, absolute value. So absolute value will eliminate the -1 to the n plus 1 and the -1 to the n. All that junk will just be annihilated by the absolute value. Okay, so you can completely disregard that -1 portion and just plug in the x to the 2 times n plus 1 all over 2 times n plus 1 factorial divided by x to the 2n plus 1 all over 2n plus 1 factorial. Then do reciprocals. Probably going to need a little more room here. So I get the limit of the absolute value of x to the 2n plus 2 plus 1 is 2n plus 3, I believe, all over 2n plus 3 factorial times the reciprocal of the denominator, that's 2n plus 1 factorial, all over x to the 2n plus 1. Then that will be the limit x to the 2n plus 3 over x to the 2n plus 1. Subtract those exponents, you get 2n plus 3 minus 2n minus 1, which will be just x squared. So I have an x squared. And then I'm going to brute force the factorials. So I have 2n plus 1 times 2n plus 1 minus 1, which is 2n, times 2n minus 1, all the way to 3 times 2 times 1. Downstairs I have 2n plus 3 factorial is 2n plus 3 times 2n plus 3 minus 1 is 2n plus 2 times 2n plus 2 minus 1 is 2n plus 1, and then times 2n and all the way to 3 times 2 times 1. So all of this material will cancel out. And with the limit as n goes to infinity of x squared times 1 all over 2n plus 3 times 2n plus 2. If you want, you can factor out the x squared now. So the absolute value of x squared, which is just x squared out in front of the limit, times the 1 all over 2n plus 3 times 2n plus 2. And this part, the limit goes to 0, because you have L over infinity. So you have some number squared times 0. That will always be 0. Okay, so the R value is less than 1 for all values of x. In other words, everything will converge in this case. And this actually turns out to be the power series for sine of x. Okay, so it's convergent for all x. In other words, the radius is equal to infinity. Okay, so it's always awesome when that happens. It doesn't happen all the time, though, unfortunately. But going back to example 3, we will need to check the endpoints for convergence in order to get what's called the interval now of convergence, right? So in the first case, example 2, the thing is only going to converge at x equals 0. Okay. The second example, the thing converges in this interval, but then we got to check the endpoints 1 and 3, okay, for convergence. In the last case, the interval of convergence is just -infinity to infinity, right? So the case we kind of have to work a little bit with is this example 3 case, and now we're going to find the interval of convergence basically. So I guess I'll call this, make this a new section, maybe 3. The interval of convergence. Okay, so again, going back to kind of these two previous examples, the interval of convergence, I'll just write IOC here, is unfortunately just 1 point, so we can just put that in a curly bracket like that. Okay, it's just the point 0. An example 4, the interval of convergence, IOC, is going to just be negative infinity to infinity. Okay. And example 3, the interval of convergence will be going from 1 to 3, but then there's a question about whether we include the endpoints. Okay, so that's kind of what we're after here in example 5. Okay, so let's take a look. So example 5, we want to know the interval of convergence for the series x to the n all over n from n equals 1 to infinity. You're still using the ratio test, so this will be the limit of the absolute value of x to the n plus 1 all over n plus 1 times the reciprocal of a sub n, which is n all over x to the n. Just cut to the chase there. Simplify, so x to the n plus 1 over x to the n is just x, and then times n all over n plus 1. You could factor out the absolute value of x, and you have the limit of n all over n plus 1, and then you could take the limit of that. It would just be the same as the limit of n over n, which is 1. So the limit of n over n plus 1 is 1, and you just get r equaling the absolute value of x. Okay? So for absolute we'll know it converges absolutely when the absolute value of x is less than 1, thanks to the ratio test. Okay? We can expand that inequality to be x less than 1 greater than negative 1. That will give us a radius convergence of 1. But then we want the interval of convergence, right? So we need to check the endpoints. And how does that work? So you're going to set x equal negative 1 and plop that value into the original series. Okay, so wherever you see x in the original series, you're going to put a negative 1. So you get negative 1 to the n all over n from n equals 1 to infinity. Okay, this thing is an alternating series, so do the alternating series test. So you have to tell me which test you're using on the actual written test. Test 4 I think we're on now. So do the alternating series test, and note, okay, for the alternating series test there's 2 steps. First, you take the limit of a sub n, which in our case is 1 over n. It's the portion without the negative 1 to the n part. That'll equal 0. And then secondly, you consider the ratio. I like doing the ratio of a sub n plus 1 over a sub n. This will be n over n plus 1. And clearly that thing is less than 1 because the denominator is greater than the numerator. So if you take a number and add 1 to it, the number that you added 1 to will be bigger, right? So n is smaller than n plus 1. It's just one of those factoids that's so freaking obvious it goes over your head. So anyways, because of the AST, this thing converges. So hence it's convergent at that endpoint. Then you go to x equals 1 and do the same game. So again, wherever you see x in the original series, you're plugging in a 1. If you were to expand this, you would get like 1 to the 1 over 1, 1 to the 2 over 1, 1 to the 3 over 1. So that series is exactly the same as n equals 1 to infinity of 1 over n, right? Because 1 to any power is just going to be equal to 1. So you might as well just write 1. What is this thing then? This thing is a harmonic series, and we know, because we've memorized it, that this thing is divergent. So we need not put anything beyond that. We could just say the harmonic series is divergent. Okay. So for our interval of convergence, our IOC, on the negative 1 we have convergence. So we put the hard bracket, and then at 1 we put the soft parentheses to indicate it's not included. Okay. Okay, so that's the deal. It's a little bit more work when this happens, and it's always kind of annoying, but there it is. Okay, let's look at another one. So we have now example 6 from the book. We have the series n equals 0 to infinity of -1 to the n times x plus 1 to the n all over 2 to the n. Let's make this the video quiz for the day. Let me mark that in my notes. This is the fourth video quiz, and video quiz set number 7. Okay. So this is section 9.8, and we're going to do example 6 for the video quiz. Okie dokie. So let's take a look, right? My R value, in this case, I take the limit of the absolute value. Again, that -1 thing, you could just flick that out the door, okay? I know in the book there, they write -1 to the n plus 1. It's redundant. You don't need to do that because the absolute value takes care of all the signs. It'll always be positive, so why not just write the expression without those? Okay, so you need not write the -1 thing like the book does. Don't do it. Okay, if you do it, I'm going to think you didn't watch any of my videos. I'm going to be ticked because I spent so much time on my videos, right? Okay, so anyways, I'm just going to put the x plus 1 to the n plus 1 all over 2 to the n plus 1, and then times, or divided by a sub n, but times the reciprocal of a sub n, in other words, which will be 2 to the n all over x plus 1 to the n. Okay. Simplifying this, x to the n plus 1 over x plus 1 to the n plus 1 all over x plus 1 to the n. You subtract the exponents, you get x plus 1 to the n plus 1 minus n, which of course is just x plus 1. And then 2 to the n over 2 to the n plus 1. How does that work? 2 to the n over 2 to the n plus 1. I'm going to bring the top downstairs. So that was supposed to be a little arrow. Doesn't look very good. So I'll have 1 all over 2 to the n plus 1 minus n in the denominator. So you get 1 all over 2 to the 1, so just 1/2. Okay. That whole thing is not dependent on n, so you could basically think of it as a constant, and the limit of a constant is the constant. So you get the absolute value of x plus 1 all over 2. Okay, so the ratio test says the thing is convergent when that R value, which in our case is x plus 1 all over 2, is less than 1. You could take that thing then and rewrite it as a compound inequality. X plus 1 over 2 less than 1, greater than -1. Multiply everything by 2. -2 is less than x plus 1, less than 2. Subtract 1 from all three sides. -3 is less than x, less than 1. And there's that'll kind of give you your radius of convergence, right? So -3, -2, -1, 0, 1. So it looks like R is 2. Okay, it's half the distance of the interval. It's this distance here. Okay, I still need to then figure out the interval of convergence. So I'll start with x equaling -3. So in my series, looking above, my series will become -1 to the n times -3 plus 1 to the n all over 2 to the n from n equals 0 to infinity. Okay. All right. Simplifying to the n times -2 to the n all over 2 to the n. You can rewrite the -2 to the n. I'm going to show you all the little steps as -1 times 2 to the n, all over 2 to the n. And then you could kind of distribute the exponent to the -1 and the 2, right? So you'd end up with the series -1 to the n times -1 to the n times 2 to the n all over 2 to the n. The 2 to the n's will cancel, right? Those are gone. And then you have a -1, -1, so you have like bases. You can add the exponents, and you get -1 to the 2n, which is the same thing as -1 squared to the n. -1 squared is +1, so you end up with 1 to the n, and 1 to any power is just 1, so why not write 1? Okay. So we have the sum of 1. So what the heck does that do? Do the nth term test for convergence. You can also consider this a geometric series with r value 1, so therefore it's divergent. But I'll go the nth term test. Note nth term test for divergence. We have the limit as n goes to infinity of the formula for the terms of the series 1 equaling 1, which does not equal 0, thus it's divergent. So thus the series diverges. Okay. All right. I need to then check the other guy, the other endpoint, which is 1. Okay, so x equals 1. And so I get the series -1 to the n times 1 plus 1 to the n all over 2 to the n. And again, you're doing some simplifications. So I have the series -1 to the n times 2 to the n all over 2 to the n. And again, these 2 to the n characters will cancel. So you end up with the series of just -1 to the n. Okay. Again, you could do the nth term test, right? So note nth term test for divergence. We have the limit of -1 to the n as n goes to infinity. The even terms will go to 1, the negative terms will go to -1. So this limit does not exist. In other words, it's definitely not equal to 0. Okay. So again, this series diverges. And so for our interval of convergence, our IOC, we'll just use the open parentheses -3 and then open parentheses 1. Okay. Okay, so that was a video quiz. Let's kind of hopefully move on to something else. Are we moving on? Oh, they gave us one more, really? You don't feel like doing that one. You could read that one. Okay. Let's look at the next one. So the next topic is doing integrals and derivatives of these series. It'll be a quick way to produce a formula for kind of an unknown function. So, I mean, you might be able to produce a power series for a certain function, but not know this other function that you want. For example, you could probably get a power series for the function of 1 all over 1 plus x. Okay, you'll be able to do that in 9.9 using the geometric series. Okay, and you kind of did it in 9.2 in the homework. If you remember, you did something similar using the geometric series. The only issue with this guy is that it's kind of useless because it's easier just to work with the function than it is to work with the power series, but it has a relationship to the natural log. So if you could find the power series for this guy, which turns out to be -1 to the n times x to the n, you could, and then if you could integrate the thing, because the integral of 1 over 1 plus x dx is just going to be the natural log of 1 plus x. If you can integrate this power series, you know, you can get a power series representation for something that has some use, because typically you can't figure out the ln without a calculator, right? But you'll be able to get this power series for it if you just integrate these power series. And it turns out you can integrate them, okay? And it's not going to affect the interval of convergence too terribly. It'll affect the endpoints sometimes, but it's not going to damage the radius of convergence, okay? Okay, so that's the kind of topic we want to investigate next, integrating and taking derivatives and integrals of power series. Okay, so I think I'm on section 4, integrals / derivatives of power series. Right. Okay. So not only is it kind of an issue with the interval and stuff. We care about that, but just how the heck are you going to integrate and differentiate a power series? Well, it turns out it's pretty simple. So if you have a power series, P of x equals the series a sub n x to the n, going from n equals 0 to infinity. There's kind of two ways, all right? You can literally expand the thing and then take the derivative term by term. So in that case, expanding it, you would have a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus dot dot dot. Then p prime of x would equal a sub 1 plus 2a sub 2x plus 3a sub 3x squared plus dot dot dot. You're supposed to be getting the series representations for these things. So how do I get the series representation? Well, you can kind of guess your way to it. You know, it's going to be some series. Looks like the coefficients are going 1, 2, 3, so just like n. And then maybe x to the n minus 1 times a sub n, some variation of that. Another way to kind of do it is just literally take the derivative of this thing, right? So if you think you have, if you take y equals a sub n x to the n and take the derivative with respect to x, here up here at the top right, you'll have n power rule a sub n x to the n minus 1. Okay, so you can kind of guesstimate what the representation of the power series is just by taking the derivative of the formula for the terms of the series, right? So you can guess it's going to be n, let me put it back in black, n a sub n times x to the n minus 1. The only issue is kind of the limits on the integral. Of course, it'll go to infinity, but that lower limit can change. Okay, so in this case, it's not going to start at 0. It actually starts at 1. And then you could kind of verify it by, you know, plug in n equals 1 and see what you get. You get 1 times a sub 1 times x to the 0, which is just a sub 1, plus, so this was n equals 1, then try n equals 2. You get 2a sub 2 x to the 2 minus 1, and it looks like we're getting what we should get. You know, we get this thing. Okay, so it's fairly simple, but there is kind of an issue with the, you know, n equals, is it 0 or is it 1 to infinity, right? Okay, you do the same baloney with the integral of p of x dx. So in that case, you know, just going term by term, starting with p of x, it'll be a sub 0x plus a sub 1x squared all over 2 plus a sub 2 x cubed over 3 plus a sub 3 x to the 4th over 4 plus dot dot dot. And again, if and there's actually a plus c in here as well, so you do have a constant of integration. But the power series representation for that, then again, you could go to this thing right here back at the top and just integrate that formula. So you're basically integrating a sub n x to the n with respect to x. So you do a power rule on x to the n. You get a to the n x to the n plus 1 all over n plus 1 and then plus c. So the power series representation formula would be a sub n times x to the n plus 1 all over n plus 1. And then again, you got to worry about n equals what, right? And then there's a plus c on there. But where does n start? So again, you could play this game of just kind of guessing. It's either going to be 0 or 1. In this case, let's say it's going to be 0, right? Because you plug in 0, you get a sub 0 x to the 1 all over 1. Plug in 1, you get a sub 1 x to the 2. So it's working. Okay, so then, you know, once you kind of stomach taking integrals and derivatives of this thing, you worry about the radius and interval convergence. So we know the radius of convergence will not change. Whoops, convergence. But the endpoint convergence may. So you're going to have to always kind of be checking those endpoints. for convergence, right? Okay, so that's kind of what they're talking about there. They give you this example 8 as kind of our playground here. So example 8, we're working with the series x to the n all over n equals 1 to infinity, x to the n all over n. And I guess we call that f of x. We want the interval of convergence for this. You also have to find the power series, the derivative, and then the integral. And there are intervals of convergence. So first let's expand this thing and see what we're dealing with. We have, maybe we should get the interval of convergence first. Okay. So you will have to get the sort of the radius of convergence for one of the guys, either f of x or the integral or the derivative. That interval of convergence, you know, you still have to find that to some extent. I think we already did this one though, right? X to the n, where are you? Yeah, right here. So the interval of convergence closed, interval -1. So the IOC for this character is -1 to 1. Let's not reinvent the wheel, right? We already know this. Then I'm going to go ahead and expand it so I can start taking derivatives and integrals. So expanding it, I have x over 1 plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 plus dot dot dot. Okay, so first I'll go ahead and get the derivative. F prime of x is going to be 1 plus 2x over 2, which will just be x plus 3x, plus 3x squared over 3, so it'll just be x squared, plus 4x to the 3rd over 4, which should be x cubed, etc. It's pretty simple to see what the formula is, but we'll take the derivative of this x to the n over n, because sometimes they get more complicated and you should really kind of get into this habit. So it would be n x to the n minus 1 over n, which is just x to the n minus 1. So that will be our formula, x to the n minus 1. And of course we want to know the starting point there, n equals what? So n equals, it looks like it starts at 1, because you plug in 1, you get x to the 1 minus 1 is just x to the 0, which is 1. Plug in 2, you get x to the 2 minus 1, which is 1. Okay, great. I'm going to have to check the endpoints for convergence, but before I do that, let's go ahead and get the integral, right? So the integral of f of x dx is going to be x squared over 2 plus x cubed over 3 times 2 plus x to the 4th over 4 times 3 plus x to the 5th over 5 times 4 plus dot 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 plus c. Then our let's do the integral of the terms, the integral up here at the top, x to the n over n with respect to x. So what are you doing? You're adding 1 to the old exponent and dividing by it. And there's already a factor of n down there, so you get n plus 1 times n. So our formula and summation notation is going to be x to the n plus 1 all over, let's put n first, and then times n plus 1. And then I need to figure out where I start, and then what I go to, plus c. Okay, so it looks like I'm starting at 1 again. So this one, it's like you could have just guessed 1 all the time and would be right, I think. Right, so if you put in 1, you get x squared all over 1 times 2, which is 2. Put in 2, you get x to the 3rd all over 2 times 3. So yeah, it seems to be working. So if you start at 1. Okay, so we kind of got our formulas for these guys. You can go ahead then and start working with the endpoint convergence for these. So first we'll start with f prime. And right now, you're going from -1 to 1. Here's 0. -1 to 1. So I need to check x equals -1. So that will be the series of -1 to the n minus 1 from n equals 1 to infinity. And so raising it to the n minus 1 is effectively raising it to the n plus first power. Those are equivalent. I just hate seeing the n minus 1 for whatever reason. It freaks me out. This guy, then, you could do the nth term test for divergence. I mean, you could do it with the other one as well, but nth term test for divergence. You'd have the limit of -1 to the n plus 1, and that does not exist because the even terms will be -1, the odd terms will be +1. That, of course, does not equal 0, hence it's divergent. Then we're going to plop in x equals 1, and we get the series n equals 1 to infinity of 1 to the n, basically, which is just 1. And again, you could do the nth term test for convergence. You could also do the geometric series. So we have the limit of 1 equals 1, which of course is not 0, hence it's divergent. And then the interval of convergence for f prime will just be open parentheses -1 to 1, so you don't include the endpoints. Let's look at then the integral of f of x, and for the analysis here you don't need the plus c portion. Okay, so we'll just basically be working on the series n equals 1 to infinity of x to the n plus 1 all over n times n plus 1. Okay, all right, so we need to look at x equals -1. So we get the series -1 to the n plus 1 all over n times n plus 1. That is alternating, so note the AST, the alternating series test. Step 1, you're looking at the limit of a sub n, which is without the -1 to the n plus 1. This will equal 0. Then you could consider sort of do a ratio test for monotonicity. So you have n plus 1 times n plus 2 all over 1 all over n times n plus 1. That'll equal n squared plus n all over top of n squared plus 3n plus 2, and clearly the denominator is bigger than the numerator, so that's less than 1, which implies it's decreasing, or if you'd rather, non-increasing. Anyways, it's convergent at that endpoint. Okay, and on a test you have to show all that work. You can't just say, oh, I think it's convergent on this one. No. Let's try x equals 1. So I have the series 1 all over n times n plus 1. I could do a comparison test, direct comparison maybe. So sure, let's do direct comparison. So for direct comparison tests, first you have to do an inequality type deal. So we can compare this. So if you decrease the denominator, you've increased this other expression. So you could just make this 1 over n squared. Then secondly, you can, what do we do? Oh yeah, so 1 over n squared, what is that? This is a p series. The p value is equal to 2, which is greater than 1, therefore it's convergent. So our conclusion, it's convergent. Okay, so at the end of the day, the interval of convergence in this case, OC, is going to be going from -1 to 1, including the endpoints. So the moral of the story is, taking the derivative and taking the integral. It won't change the radius, but it will change sometimes change the the endpoint convergence. And you can see all three of the intervals are different. Okay, so anyways, that'll do it for us. Thank you for watching as usual, and I'll see you next time.